Okay, last lecture we have shown the achievable part of the multiple access channel. Therefore, we have to show also a converse. And for the converse, we will show this for R1. So we did it like we always start. We knew n times R1 is lesser equal than the entropy of W1, and then we extended this in such a way that this is lesser equal than the mutual information between W1 and Y1 to the n. Then we add here a condition. Instead of yn, we write here the joint distribution here that makes the mutual information bigger. Then we can condition this mutual information on W0 and W2, which doesn't change here anything, because W1 is independent of W0 and W2, and here you have this joint distribution of it, and therefore we can leave it out also here. Then we can write this as the sum of the entropies, so this is equal to the single mutual information here, and we can write this as the sum here. That's the formula for this here. And then you see here that's the entropy of yi and yi minus 1 and W0, W2. Here's the entropy of yi under the condition yi minus 1, W0, W1, W2. Now we thought what we can replace. So here we add x2 to the n. This we can add because this is just a function of W2 and W0. So it doesn't change the value here. Here we know that yi doesn't depend on yi to the minus 1, and x1 and x2 are functions of W0, W1 and W0, W2, and we can replace here this with this. So we are back with this formula. Now we leave out here this condition here and this condition here. So we make it bigger. Here we take the same like before. Then we have the sum over this entropies here. But this entropy here, we take the formula and we get the mutual information of x1i and yi under the condition x2i and w0. Now we introduce a random variable u, which is a joint random variable of W0 and I, where I is an independent random variable of all other variables. And we choose the distribution of pi a equal 1 over n, for a equal 1 to n. And then we can define x1 as x1i, x2 as x2i, and y as yi. So we have the following factorization of this joint distribution here, which we choose. And we get that R1 is lesser equal than the mutual information of x1, y under the condition x2 and u. You see why we introduce this. Then we have here always the same values n times, and it's this I as the distribution 1 over n, and therefore we are left with this rate here. The same can be done for R2 and also for R1 plus 1 plus 2 and R0 plus R1 plus 2. And we have these conditions here. And using all these conditions, we get really the MAC region where we show already that this is also achievable. So again, we consider the case for R0 equals 0 here. It's a little bit less work to write this down. And then there's another comment here for R0 equals 0. It was originally shown by Alswede, and Alswede showed it not with this auxiliary variable u. He just showed without an auxiliary variable, but then we get the convex hull of this region here. So some people like more this version because you don't have to take the convex closure over this, but you have this auxiliary random variable. Some people like more this version because you don't have to use this auxiliary random variables. So these are two possible versions of the Mac region.